saben ustedes, estas dos sesiones son sesiones preparatorias para los cursos intensivos del programa de Twinning de la próxima semana con el Observatorio del Aire. Antes de comenzar varios comentarios y en español que queden bien claros para todos. Es muy importante que el lunes lleguen a las 8 de la mañana para que podamos hacer la inscripción oficial en el curso. La inscripción no los compromete a participar ni a ganar el curso. La inscripción lo que hace es, bueno, comprometerlos, digamos, hacerlos sentir que están dentro. De modo que es muy importante que estén en ese momento para que lo hagan. Quienes definitivamente no quieren comprometer de ninguna manera, pues no lo hacen. Sin embargo, tengan en cuenta que los que se inscriban y eventualmente se den cuenta que pueden ganar el curso, pueden obtener una electiva y además en su hoja de vida va a tener un curso internacional, digamos casi de nivel de posgrado. Es muy interesante que se inscriban y que estén ahí. No se limiten, después se arrepienten si no están. Bueno, pero eso no quiere decir que eso sea obligatorio para todos los que integran. Bien, ¿qué más? Hoy estamos haciendo pues unas pruebas, principalmente son pruebas, digamos, de todos los recursos de video, que veas que esto quede grabado en video y en general, digamos, el funcionamiento del curso. Es muy importante que nos ayuden a verificar que todo esté en orden, para que en el momento en que hagamos esto, ya con los profesores extranjeros, pues todo salga bastante bien. Excelente. Déjalo por ahí. Muchas gracias. No, este es un laboratorio portátil de matemáticas que conseguimos especial para... No, estos son los parlantes de aplicación. Ayer nos dimos cuenta, por ejemplo, la clase de ayer quedó grabada en video, pero el audio no es muy bueno. Entonces le decía yo a Rafael que es mejor que haga una amplificación del audio. Okay, so the most important thing today is that you ask anything that you think you have to ask. It's very important to ask, it's very important to talk if you want to start to think and to work in English. It's not hard after you start. It's not hard. The hardest part to listen and to talk in English is start. And without being shy. I can speak in English, in my Paisa English, English, yes, because I'm not shy. I'm not shy. Okay, I have overpassed all my complexes in the past, so I just started. Okay, so please ask. Okay, today we will review some topics about what do we need to know about mathematics for the courses we will see next week. Obviously, in 1 hour and a half, we cannot review and we cannot learn at all anything that I will review here. If you don't know calculus, if you don't know differential equation, it's very hard to learn that topic just seeing at a slide. But in any case, it's better if you see a differential equation, for example, next week after seeing it in this slide. So this is my bet with you, trying to get used with some of the concepts we could see next week before arriving with the international professors. Okay, the outline of this class. Yesterday was the class about physics. This is the outline of this class. It's very simple. It covers a lot of information, but packed in a short presentation. Okay, we will see very fast because you are very well at this. Some concept about the powers of them, the usage and the operations with scientific notation. Then some concept about spherical geometry. Then calculus, integration, special, differential equation, and spaces of functions, which are very important. This is a very important topic, especially regarding the concept of Fourier transform. That is very important when thinking about, for example, spectral analysis and things like that, which are very important in astrophysics. Okay, let's see what can we say about all these topics. Astrophysicists are probably the professionals in the world that has the best relationship with large numbers, large and small numbers. Astrophysicists doesn't work with the small numbers like 27 or 3 or 5,000. Astrophysicists work with 10 to the 17, 10 to the 17, which is probably the size of the universe, 10 to the 24, 10 to the 20, to the 10 to the 10 to the 2, which is probably the size in kilometers of our universe, and things like this. These are the numbers of astrophysicists. We are not concerned with the small numbers. So, it's very important for any astrophysicist know how to work with this kind of numbers. And, okay, don't feel any fear about these kind of numbers, because these numbers will be very, very common in the world as an astrophysicist. Okay, what do you need to know about these kind of numbers when are working in astrophysics? You need to know about these numbers. How can you manipulate them to calculate things like you read in the presentation? For example, it's very easy. When you ask if Spanish arrives, don't worry, because Elena Rossi, for example, is Italian. So you say several words in Spanish, maybe she can understand you. Okay, Bernard cannot understand you at all because he is German, and German is impossible. It's a very different language. Okay, so how many protons are in the universe? For example, this is a very important question for cosmologists. For example, how many light bulbs can you can turn on? I'm sorry because of how the sentence is written, using random signals from the center of the galaxy. This is a very very interesting question. How many hydrogen atoms are between me and the center of the galaxy? Which is the volume of the observable universe? All of these are questions that, although they seem very strange and very curious and just useful at outreach is a very important word for me. Anybody knows what outreach means? Outreach. What means outreach? Outreach. Where are the classes? What is that? In English, what outreach is? What is outreach? Out of reach. Out of reach. Okay. You are analyzing the world, the origin of the world, but this world has a very precise. No, it's not out of range, but it's outreach. Outreach is.
So astronomy to the public.
Yes. Outreach is the
popularization.
Yes, it's the word we use as divulgación in Spanish. Divulgación. It's not there is not a divulgation in English. Even popularization is very French, but in English you see or you say outreach
or the public education.
public location, okay, public informal location. So many of these questions seem to be questions for doing outreach, not for doing astrophysics, but as Paulo, for example, can say, even me, many of these questions could arise even during research. So let's see how good we are, for example, for computing the volume of the observable universe. Can you compute how many cubic centimeters has the observable universe? Can you? So let's try to compute the volume of the observable universe. Okay, and the rest of the questions are homework. Okay? So you have to compute how many light bulbs you can turn on with it. Okay, let's see. Ah, this is terrible.
No, look. Features.
It's
There's
oh, broken. Oh my god. So I screwed up. You're racing. Okay, let's see. I need ideas. How many? Which is the observable, the volume of the observable universe? Okay. How can I perform this calculation? What do I need? What do we need to calculate the volume of the observable universe? What?
The farthest point.
The farthest point, the point which is at the largest distance from the Earth. Okay? So if we are here at the Earth or at the Milky Way, if we work at the galactic scale, so we need the farthest point from the Milky Way. Which is the farthest away point from the Earth? Where is the farthest point from the Earth? Maybe Andromeda Galaxy? Of course not. Maybe the Virgo cluster? No, Virgo cluster is actually just in the neighborhood.
Just for our time.
No, for a radio telescope, or probably even for a telescope in the space. Which is the farthest point? Santi?
Well, there's not quite. Well, there's not. You could say if the universe has existed, if the Big Bang occurred 13.8 billion years ago, then the farthest we can see is 13.8 billion light years.
Say 13.8 billion light years. Okay, but this is okay. 30.8 billion years is a distance in time, which is right. If you talk in astrophysics, you can use time to refer to a distance. When you add the word light year or light before year, you are compromising your knowledge about astrophysics, because light could travel 13.8 billion years, but while light travels to the Earth, this point can move, can be moved. So the point is that this time, the distance in time, not necessarily in cosmology, is a distance also in space. Okay, but we can assume this. We can calculate the volume until this point, a point located at 13.8 billion light year. Okay, now we have a distance.
Something that is true about that is that this is the farthest point that you can see.
In time, but not in the distance. Light years now, because of the expansion of the universe. Because of the expansion of the universe.
Of course, that point is not right now at the same point.
Yes.
Because the expansion.
Yes.
That is okay.
Yes.
You can say
very good. You know, this is another point when you are asking. You have to think in what you are asking, not think in English. Don't think if you are speaking well for your classmates, I'm sorry, I'm paisa. No! If you don't think on what you are you are actually asking, you will seem more stupid than simply. So please ask even with mistakes in your English. Please just ask. I mean, because for example, as you can see, with Paul we were talking. We were not thinking about what we are talking. So the way we are talking. So please, don't be shy.
Sometimes in English I have seen that 13.8 billion years, they refer to billion and 2,000 million.
Okay, yeah, this is a very important point I want to grasp right now. So, I have a distance, but I need a volume, not a distance, a volume. What? We need a shape, of course, because the volume depends, as LaRue's dictionary has taught during years, that if the universe is cubic, it will have a volume. But if the universe is spherical, it will have a different volume if it's flat. So, what is the shape of the universe? What is the shape of the universe? Spherical, cubic, a cylinder, irregular? What is the shape of the universe? What do you think? Please say something. Say cubic, say spiral, say anything. Say anything. What do you think? Which is the, according to pictures? See? Spherical. Yeah, very good, very good. So, we will assume that this is spherical, but that's because the universe is isotropical. Isotropy is the key word here. Isotropy. Isotropy means that the universe is the same in every direction you see. So, if the time is 13.8 million in this direction, seeing to the north, for example, here, why it could be different when seeing in this direction? It should be the same in any direction. If there were a difference, the universe would be very special, and you can see more galaxies in one direction, less galaxies in another direction, and that's not what you are seeing. So, because of this isotropy, you will assume that the universe is spherical. So, if the universe is spherical, I will do this plot smaller. Put here a radius of 3.8 billion light years, which that is the same that giga light years. Giga is the same as billion in English. Please, Mauro.
Can you explain us
Yes.
what is the difference between isotropy and
Homogeneity. Yes, there is a difference between isotropy and homogeneity. Okay, homogeneity. Okay, the difference could be explained, for example, saying this. For example, the water in a pool is homogeneous. It's homogeneous. It's the same. The density of the water, probably the temperature, and many things are the same in all the water in a pool. Okay? But the pool is not isotropical. Why? Because the pool normally is larger in this direction than in this direction. So the water is homogeneous, but the pool, or the water in the pool, is not isotropic. Okay? So it is different. Homogeneity means the same in any point, at any point, the same density, the same property, but it doesn't matter how is the shape of the way the matter is distributed. But isotropy is the same in every direction, and they are not the same. You can have something that is homogeneous, like a pool, but not isotropical. And you can have something that is isotropical, but not homogeneous. For example, the Earth is not homogeneous, right? The Earth is different according if you are in the surface or in the core. But if you are in the core of the Earth, you see something isotropical. And at any point you will see the same matter, almost the same density, the same density profile. So from the center of the Earth is isotropical, although the Earth is not homogeneous.
Maybe I think the difference is because isotropy is related with the shape or how you see something.
Yes.
And homogeneity is related with intrinsic properties. So,
okay. There are a lot of ways of explaining this. So I don't know if it's good to remember. There is a word in this session. This session is very experimental. Okay? We are not doing any academic. You will not have a title because of this. Not, neither a score in linear algebra. So the key word here is fake. You know what is fake? I explained it yesterday. Fake is a lie. It's a mentira. It's falso. It's falso. Please, if you know what I'm telling you, please ask. In any case, ask. Just for ask. Just for training your tongue. Just for training your listening, your conversation. Okay, so we have 13.8 billion light years, and we need to compute the volume of this sphere. What can I do? So, this is very important. You will compute how many cubic centimeters are in the universe. This night, tonight, when you arrive to your home, you will explain to your mom, Mom, now I know how many cubic centimeters are in the universe. Oh, your mom will give you money for the rest of the semester because, okay, you are doing very well. So please, pay attention.
third.
Okay, yes, so we need the volume
Yeah.
of a sphere, which is
4/3, I guess.
4/3 multiplied by p,
ER.
multiplied by the radius of the sphere
Yeah.
to the okay. This formula is very expensive for the brain. This is too expensive, and I don't recommend you to remember all this stuff. If you are a good astrophysicist, or if you are a good physicist, you know that pi is more or less 3, and 3 cancels with 3. So the answer is that the volume.
Why you say that?
If you just complain in Spanish, I will not hear. Please complain in English. Machete. There are a lot of Mexican words. In English. So it's much more easier. It's much more easier to remember 4 multiplied by the radius to the third. That remember this formula. Okay, of course this formula is very important, but this is in Wikipedia. So you should not concern about this. You should concern about the fact that the volume is 4 times the radius to the third. This is what you have to have in your brain. This is the way I think about the universe. Okay, so we need to calculate this number. So now I have the R, but the R is expressed in a very strange unit, light years. What the fuck are light years? Okay, this is not a word that Elena will use, but I say words, bad words, even in English. So what the fuck are a light year? 1 light year. Well, how many centimeters are 1 light year? Please tell me this. Tell us, how many centimeters has our one light year? You don't remember, but you can tell me how can I calculate this? Oh my God, you are calculating your brain in your mind. Please pay attention. Pay attention. We need to return to the chalks, little chalks. Yes, and blackboards, really blackboards. We need to come back to this time to throw off the chalks. Okay, so how many centimeters is one light year? While you're thinking, this is the most difficult mathematics for physicists and for astrophysicists. I have seen colleagues of mine that are able to do spectacular mathematical tricks, but are not able to work with numbers. Isn't it crazy? And I swear to you,
light year is 9.46 billion kilometers, right?
wow, yeah. You have the number. Number is something like 9 or 10, close to 10 billion kilometers.
No, it's 9.
So,
How can you compute this? How can you compute how many centimeters? Listen to me. I have seen teachers, students, astronomy students, that in a class of astronomy, giving a class of astronomy to children, ask how many is one light year, and the astronomy student says, "Oh, I'm sorry, I don't have here Wikipedia. Oh, I forget my this piece of paper where I have the constants." No, you have to know how to do this. Please, anything you have to say, you have to say, please, hands, raise your hand and talk. Hello, please. In English. So. 18 centimeters. 10 to the 18 centimeters. What you will learn in the following 2 minutes is very important for your life. So it's very important to be concentrated.
I think the idea is that we pay attention to our hair. He said we try to calculate. So at this point, we must say that for calculating the light year, we have to take account to what we know. We know that a year has 365 days.
You know that a year is 365 days plus something. This is a year. Days. This is days. But we need a light year in centimeters. So it's very bad to give an answer in days.
So you keep converting until you get to centimeters.
Okay, and how can I convert days into centimeters?
days,
You can use the
Okay, no. Okay. Let's see the. Let's follow our order.
So you can take 300,000 kilometers.
Okay. The speed of light. Not the velocity of light. It's the speed of light. It's different because velocity is a vector and speed is an scalar. So it's the speed of light. The speed of light is 300,000 kilometers per second. Okay? So we have second here, days here, so we have some future. You know, you have computed this, so I need that you recomputed this with me in English, please. So this multiplied by this, but you cannot cancel out days with seconds, so
You can take multiply for 3,600 to know hours, right? And then
okay, so each day have 24 hours.
Yeah, and
Each hour
3,600.
2,600 seconds. Oh, very good. So, please, pay attention to this calculation. You cannot use a calculator in front of a group of children. Oh, let me use my calculator. Fuck! You are the summer. Please give us some examples. So here is where you have to be very clever at using numbers. So 300,000 kilometers is in scientific notation, as you know, 3 times 10 to the 5. Okay? This is okay because these are 5 zeros and this means 5 zeros. But this is kilometers and you need centimeters. A kilometer is 1,000 meters. Okay? And a meter is 100 centimeters. Okay? Very important. So, look, this is the velocity of the speed of light. The speed of light in centimeters per second. Okay. Let's continue. 365 is actually 400. And this is the trick. If you use 365, it will take a lot of time calculating anything. You have to be very practical. And this is very important because any paper in the world starts in a piece of cheat, in a notebook, in the margin of the notebook. Each paper in the world starts with a very small calculation where you round up all your numbers. These calculations are called back of the envelope calculations and are very important for real scientists. Engineers doesn't use it, so it's a secret. It's a secret among us. Engineers are not able to use 400 instead of 365 because engineers are very strict. But scientists are practical. And the practical thing here is replace 365 by the closer number. 24 is, how much is 24? 20? And how much is 3,600? 4 times 10 to the 3. So now you are able to multiply. This is very easy to multiply this. Okay, so let's please first we need to join all the power of 10. The power of 10 is 10, 5, 8, 10, 12, 13,
16.
and 16. 16. Yeah. Now I have the order of magnitude. It's 10 to the 16. When you say that it's 10 to the 18, so what happened? Let's see. 3 times 4 is 12. And 12 times 2 is 24. And 24 times 4 is 80.
96.
Oh,
It's 96. Okay, it's 96. Ah, you are very good at multiplying.
Yes.
96 is 96.
Yes.
Yes, it's 96 multiplied by this. Centimeters. And now you have the number. The number is 9.6 multiplied to, because this is 96 is 9.6 times to 10. So it's 2 to the 17 centimeters. The right answer is 9.46. 46.
Yeah, 46. Okay.
So you think that this is a difference in 10 to the 17 centimeter? No, this is not a difference. This is the right answer. So the point here is that if you are able to convert this into this, you are becoming an astrophysicist. So please be practical. Be practical. Programs will do in the right way, but if you are in front of children and you have to do in your mind, a lot of children think, oh, this guy is big. Okay, he can pull out a number from his head, and you are doing all this stuff. All
I
right.
have a problem with that. We need to know, for example,
Okay, okay.
En la época más temprana.
Did you understand? Did you understand that? The earliest time. Okay, the earliest time.
We need all of the numbers.
Oh yes, yes, of course you need to remember things. Not the worry, don't worry about it. You need to remember things, but a few things. A couple of constants. I can remember, for example, 5 constants of nature, no more. And I cannot remember any number, any name. I cannot remember the name of any of you. And just with 5 numbers, I can calculate anything in the universe. Please ask. Ask. I can calculate anything with five numbers. Okay? So please remember 5 numbers. Oh, yeah, okay. You don't really with me. Ah, okay.
My English is so bad.
No. Your English is good. And I swear, your English is good. The problem is probably that you are thinking more with your English. That is your question.
So my problem is about the precision.
Okay, the accuracy or the accuracy of your.
We know that the blank age is
Yes.
to the
10 to the minus
masters,
43.
or I don't know, but that's so precision.
Yes.
What happened with that? We need to calculate some things with.
Yes. Okay, this is part of your. This is mathematics, and my friends. Mathematics are not about knowing how to integrate in 3 dimensions and how to calculate a Fourier transform. Mathematics is know how to work with numbers. Plainly that. Numbers. If you are not able to work with numbers, please don't try to integrate anything because you don't understand anything. Newton invented calculus first calculating with numbers. So you have to start with numbers. It's plain numbers. So one thing you will learn, Mallory, with time is which accuracy, which is the degree of accuracy you need to calculate something. In this case, for example, if we assume that this number actually is just 10 to the 18, the result will be good inside probably one order of magnitude that for your mom will be okay. So we are computing a number for our mom. Okay, today is Mother's Day. Okay, Mother's Day. You will bring this to your mom. So let's continue and finish with this. So now we have the number of centimeters. 1 light year but I need to calculate how many cubic centimeters have the universe. So, what is the next step? There are people here that have already seen differential equation. And maybe they are very bored calculating the volume of the universe. But I'm asking right now if they have calculated sometime in their lives this number. If they have not calculated this number, differential equations are trash. Simply because you are not have a relationship with numbers. So, which is the next step? I have 1 light year.
Maybe knowing the radius of our sphere.
Okay, the radius is 13.8 billion of light years. So, the radius of the universe is 13.8 times billion. A billion. How much is a billion? A billion is 10 to the 9. Yes? Okay, it's 9. It's incredible because B for Spanish people is 2 times B is 2 times 6. B is 2 times 6. Million is 6. And billion is 2 times 6. It's twice 6. Thank you very much. But for people talking English, and people talking in Portuguese, billion is actually 10 to the 9. 10 to the 9. So it's 13.8 times 10 to the 9. This is the size in light years multiplied by the number of centimeters that 1 year has, which is 10 to the 18. So in this case, which is the answer? Which is the radius of the universe in centimeters? Is 1.4 times 10 to the... Please. Share with us.
No, I was saying that I have no idea it was 10 to the 9.
What? It's not universal, it's not worldwide. Not this 10 to the 9. 10 to 9.
So how did they call that? 10 to the 12?
Yeah.
It's not 10 to the 12. It's not 10 to the 12 because it depends on the standards. And this is called the short count, and this is the long count.
Yeah, but how Americans or British call 10 to the 12?
Trillion. Yes.
So this
You know,
They put each 3 zeros.
let me give you an example. When you see a book of astronomy and they start to read the names in the book of astronomy, the names of constellations, oh my God! You see in the book, in English, book of astronomy, you have a lot of explanation of how to pronounce, for example, Sagittarius. Sagittarius, for them, Sagittarius, it's a very strange word. For us, Sagittario is Sagita, y Sagita is Sagita. Algo sagital. Have you heard this expression? Something that is sagittal. Spanish is very close to Latin. English is not too close to Latin. So for English people, B is not 2. And this is the point. For us, it's very confusing because B is 2. Okay? Bisiesto, 2. Okay, so it's 10 to the 9, and okay, I have given you enough time to compute how these numbers add up. What is the answer? To the 927 centimeters.
Oh. That's the 8. Yeah, because...
Yes, very good, because if you convert 13.8 to 1.4, you're adding a 10, so it's to the 28. Look, this number is huge. This is the number of centimeters from here to some point located at. But we are not ending this problem because we need the volume of the universe. The volume. This is the size, but not the volume. So to calculate the volume, what do we need to calculate?
You can just replace the 4. You know the 4, you know the 3.
Yes, no, this not. You just need to know 4 multiplied to 1.4 to the 10 to the 28 to the 3rd. Yes. Centimeter, the centimeter, and the number is 1.4 is almost 1. It's almost 1. That 1 to the 3rd is very easy to calculate. But actually, no, you're right. You're right. 1.4 to the 3rd is not 1. Okay. Now I need to request you to don't talk too much. Okay. Just be quiet. Just a minute. Just a minute. So I will assume that this is not 1.4 to the 3rd is not 1 but 2. So if you assume that this 2, this is 2 multiplied by 4, and this is 8 to the 28 multiplied by 3 is 24 and 84 cubic centimeters, which is a huge number.
Wait,
It's a really...
1.4 to the 3?
1.4 to the 3, my best guess is 1.
Okay.
But I know that you are very. So I think that it's not one but two.
So 2.
You calculate. You have the gun.
Okay, but if you take that 2 to the 3 is 8, right? And then you have to multiply for the other 4.
No. 1.4 to the 3 is 2 for me. And I replace 2 multiplied by 4. And the answer is 8 times 10 to the 84 is cubic centimeters. So the answer for your mom this night is that the universe has 10 to the 85 cubic centimeters. Oh my God, a lot of Coca-Cola 2-liter bottles. A lot. You know, in the universe exists approximately 10 to the 80 protons. Think how many protons, how many electrons do you have in your body? A lot of protons. And in the whole universe exists 10 to the 80, which is 100,000 less than this. So this is a lot of cubic centimeters. This is mathematics. This is mathematics. You think that this arithmetic and this is plainly stupid, but if you are not able to compute this, don't try to solve a differential equation. It's my experience with colleagues, and my experience with the students. Please, first you have to see the numbers. Okay, spherical geometry. This is another topic you need to learn to be an astrophysicist. But you don't have to know all this stuff about trigonometry, identities in the sphere, and maximum circumferences, and all this stuff. No. You don't have to know this to be a good astrophysicist or to understand the next 2 weeks. But you have to learn, or you have to know just one thing from spherical geometry. One thing. Do you know what is a steroradian? Do you know what is a spherical angle? Do you know what is a spherical angle? Oh my friend. Spherical angles are the nightmare of astrophysics students. Spherical angles. So let's see, and this will be the first hard thing you will see in the first course next week. When this Italian girl, start to write this thing, and you see, oh my God, until here, I have understood anything. If you see this, what kind of thinkings, what can you think if you see this thing? It's very simple, and many of you know what a spherical angle are, but it's interesting to review it in English. What a spherical angle is? So, you can remember what a plane angle is. And what you remember of a plane angle is how it's called in English. This instrument. Do you know this instrument? No, this is a compass. Okay, guys. Prod is a compass. In English, prod is a compass. Protractor. Okay, this is the word. Protractor. Do you know the protractor? Yes, okay. So, protractor, which is in Spanish is transportador. Okay, this is the name you use to measure, it's the name of the instrument to measure angles. Okay? And you measure angles with the instrument. If somebody asks you, what is an angle? You probably say, okay, an angle is what you measure with a protractor. It's something inside a triangle. This is the universal answer. It's science zero. You don't have an answer when you are asked what is an angle. But the angle has a definition, a very proper definition with a circumference. And the definition of an angle is the ratio between the length of the arc and the radius of the circumference. So you have a circumference, and this is the length of this arc, and this is the radius, and the ratio of this number is the definition of an angle. The definition of an angle is the circumference. Okay? This is the definition. The angle is the ratio between the two distances. The most interesting thing about angles is that they don't depend on the size of the circumference. If you shrink circumference and divide this new length by this new radius, the ratio stays the same. And that's why this ratio is very important in mathematics. That's why this number is important. From here, it comes that the total angle of a complete circumference is which is the angle of the complete circumference?
300 degrees.
Okay, 360 degrees, which is the bad way to measure angles. Because 360 is very arbitrary. Very arbitrary. If you go to an extraterrestrial civilization and ask them what is the size of the angle of a complete circumference, they will not say 360. They will say 5,000. Oh my God, these guys are wrong. Have you studied the universe? 5,000? This is impossible. So the right measure of the angle of the full angle is this. The full angle is the length of the full circumference that any toddler knows. In the kindergarten, we know that the length of a circumference is 6 times the radius of the circumference divided by the radius of the circumference. The result is 6. The measure of this angle is 6. If you go to any extraterrestrial civilization and ask them which is the angle, they will answer very fast 6. This is a full circumference angle. 6 what? 6 nothing. 6? Since the angle is a ratio of two quantities with the same unity or the same measure, you will not have anything with measures. So this is a number, a pure number. This is a constant of the nature. This is a constant of nature. It's a pure number. But some guys in the history of humanity, I call them radians. I hate radians.
Radians is nothing.
Radians is nothing. Radians is a way to be more smart in front of girls and things like that. Okay, I know what 6 radians are. You don't know what 6 radians are since you are using radian as a word. Okay? You know, the full angle is 6. The full circumference is divided in 6 parts. Not 360. Using this definition, we can define the solid angle. Solid angle is an angle in 3 dimensions. So instead of a circumference, you use a sphere. Instead of an arc, you have a region of a sphere, a patch of the sphere, probably a country in the and the solid angle is the content in 3 dimensions of this cone, or of this figure, this strange figure that you create here. You know, when you use how do you say linterna? Light. Okay. A linterna. When you use a linterna, yes, a light, and you use a light coming from the light. Lantern, okay, bring a lantern, green lantern, okay. And when you pour out light from the lantern, the light goes in this way, creating a spectacular spectacular cone of light. Okay? The measure of the content, of the angular content of this is called solid angle. And as you expect, solid angle is the ratio between the area of the patch divided not by R, but divided by the square of R. This is the definition of a solid angle, the solid angle. Okay? So, the same question. What is the solid angle extension of the full sky? How many solid angle? How many anything? If it's the ratio, it doesn't have units. But in any case, somebody call this esteroradians. Esteroradians. Because estero means 3D. But this word is just to get some girls and some boys. This is just for fun. A is the area of this patch. Okay? So, the full sky. How many steroradians have the full sky? If you want to get the full sky, you need to divide the area of the full sky, what is the area of a sphere? Is 12 multiplied by the square of the radius. Okay? 12. No, not 4 pi. 4 pi is again just for seem more intelligent. You say 12 times the square of radius. And if you divide by r square, the result is that in the full sky I 4 pi or 12 steroradians. 12 steroradians. Okay? If I pay attention, this is for the exam. For the exam tomorrow. Tomorrow I will send you the email and exam. And the exam say, okay, I have seen in the sky the coma of a comet. The coma is the atmosphere of a comet, covering a solid angle of 3 steroradians. The question in the exam is, do you believe me? I have seen, I'm very intelligent, I have seen in the sky a comet, and the atmosphere of the comet in the sky have an extension, an angular extension of 3 steroradians. Do you believe? You don't believe? What about it? No? Do you believe me? 3 steroradians for the comet? No? 3 steroradians is too much? Or is just a few? It's too much. It's too much. This is another thing about mathematics that we need to know as physicists, as an astronomer, as astronomers, as mathematics. Numbers do not mean the same in all contexts. 3 is too much when thinking about steroradians, because the whole sky is 12. So 3 is, oh my God, it's a quarter of the sky. So this part of the sky, from Bello to Santa Elena to the middle of the sky, is 3 steroradians. Okay? So be delicate with this kind of ratio. Good. This is the only thing you need to remember until 80 from spherical geometry. What do you need to know for sure about calculus? Do you have to know how to calculate the derivative of sine, or the derivative or e to the sine of logarithm of x? This is what you need to know? No. This is a way to maintain you occupied the whole semester. The only thing you need to know about calculus, this is calculus compressed. Okay. Is what Newton teach us to physicists what calculus is. Since Newton up to date, calculus has changed a lot and has become something very, very difficult to understand. But in the time of Newton, and very boring. But in the time of Newton, calculus was almost physics. And physics is very nice. Okay, this is the problem where calculus born. Okay? The problem where calculus born was Newton was asking how large is the force that this marker feels coming from the Earth? What is the force that the Earth create or produce on this marker? The answer is very simple for anyone that has seen the kindergarten, because if you put the Earth here and you put here the marker, the only thing that you need is the distance between the marker and the Earth square. You need the mass of the Earth, the mass of the marker, and multiply by some constant. This is the force. This is the magnitude of the force you need. Okay? But the point is that what we don't know is that Newton proved this formula just for things that are very, very far away from from the other. For example, for the Moon, for the Earth, and for the Moon, this formula works perfect. This formula can be used just if the distance between the objects are much larger than their sizes, but not in this case. You cannot use this formula in this case. Oh, okay, at least in the time of Newton. Why? Because the Earth is too large. Too large. So, when you say this distance is the distance to the surface, or the distance to my grandmother's house, or the distance to Australia, what is this distance? What is this distance? You know the answer. Yes, the answer of Newton, but after working hard inventing calculus, this distance is the distance to the center. But why? Why? So, the way as Newton solved this problem was thinking on Earth not as a big object, but as the summatory of a large number of small objects. What Newton did was divide the Earth in small chunks of matter and calculate the force that each chunk of matter produces on the pencil. The answer of Newton was, if we want to compute the force that the whole air produces on the pencil, what you need to compute is the force of each chunk, and then you need just to sum up all these forces. But the problem is, in how many chunks of rock can you divide the Earth? The chunks should be of the size of a mountain, or the size of a rock, or the size of a grain of sand. What is the size of these chunks of matter? And this is the origin of calculus. The answer of Newton, or the answer of mathematicians along these centuries, is that the size of this chunk is very small. This is the answer. Very small. How small? So please think in something very small, and the answer is more small than that. 10 to the minus 43 centimeters smaller. 10 to the minus 80 smaller. When something is smaller than the smallest, it's called a differential. This is called a differential. Many of us, when attend classes of physics or classes of astrophysics and see this stuff everywhere, because you will see this. I have seen already the first slides of the first class of the course, and it's full of this. So be prepared. Be brave, because you will see a lot of things. But don't worry. This is very simple. This is small, something very small. In this case, this is a piece of volume, a volume. The volume of this chunk is very small, very small. So Newton said, okay, I have a very small chunk of matter with this volume, and how how much is the mass of this chunk of matter? The mass is simply the density of the matter multiplied by its volume. Density by volume gives mass. But since this is smaller than the smallest, this is also smaller than the smallest amount of matter you can think. So Newton thinks that actually what could go in this formula is this dm. But if you put dm here, this is not F, but dF. This is the amount of force that this chunk of matter produces on this pencil. Okay? If you understand this, you have understand 20% of calculus. Okay? Probably you think I'm crazy, but you know, I have been in physics for 15 years trying to explain to engineers this kind of stuff. So please take, okay, believe me. Okay, so, but the question now is how much is the total force? How much is the total force? And the answer is very simple. The total force, actually, you have to sum up as vectors. So you have to put here the unitary vector and a minus, meaning that is attractive. And to compute the total force, the only thing you need to do is sum up all these terms. Sum up all these terms. From 1 to what? From 1 to what? Since these pieces of matter are very, very small, the amount of pieces actually are not finite. But are infinite. So this sum is infinite. This is an infinite sum of terms, and if summing up 100 numbers, 1,000 numbers is hard, you can imagine how can you sum up an infinite number of terms, an infinite numbers of numbers. Fortunately, Riemann existed in the history of calculus. And Riemann demonstrated that we can calculate this summatory, this sum very easily if this formula is also very easily mathematical. When you use the techniques developed by mathematicians during these centuries, you convert this Greek letter in this Latin letter, which is an S. You know, it's an S, like example. Okay? This sigma is converted in this, and you get this beautiful and incomprehensible expression, which is the total force that the air produces on a pencil. This is calculus, no more. Calculus is about calculating infinite number of a sum with infinite number of terms. If you think in derivatives and if you think in differential equation, actually you are thinking about calculating integrals in different ways. Everything in calculus probably is about calculating integrals. Actually, there are things about derivatives that are very important, but integrals are the most important thing probably in calculus that you need to know when thinking in physics and thinking in astronomy. Integrals. Okay, so, but there is some part of calculus that are very important to know. For example, so you will see, for example, on Monday, you will see this expression, for example. And on Monday, you will see this expression. And when you see this expression, you will be crazy. Oh my God, I knew it. This course is not for me. I don't know calculus, I don't know how to do an integral. Oh my friend, please kill me. God, kill me. No. What this means is a sum, and this is what goes inside the sum. You are dividing something that can be just computed for small things in small parts, and then summing up each contribution until obtain the big thing. It's just that. Please don't be afraid. If you need to calculate this integral, you can ask some slave. You can go to the building 4, ask for an slave. I need a slave that knows how to integrate, because I don't know how to integrate. And please integrate it, because I understand this. I understand this. The relationship with mathematics should be like this. Mathematics is something to solve problems. Mathematics cannot be a nightmare. So let's think about other ways to express integrals. There are other ways to express integrals that are very, very popular and are called differential equations, which are also the nightmare of physicists and astrophysicists, but they are integrals. Simple integrals. The most okay, this is a terrorist attack against somebody. Thank you. Thinking this is the most famous differential equation, and the most famous differential equation is actually an integral. The most famous differential equation comes from this formula. The amount of space that a body moves is velocity or speed multiplied by time. You know this. This is very easy. This is kindergarten physics. Okay? Yes. But what happens if velocity is not constant in time? You cannot use this formula. If velocity or if the speed varies with time, you cannot use this. Because if you use this, the question is at what time you compute velocity. So actually, if velocity changes with time, you can only multiply this velocity by a little amount of time around the time when velocity has this value. How big is this quantity? It's smaller than the smallest. And this gives you just a small distance travel. Okay? So this expression can be converted very easily using the idea of Newton in this expression. Ta-da! In English it's ta-da. Yes? The distance traveled by a body having a very complicated velocity. It's just the sum of the small distances traveled in the middle of the. This is an integral very easy to understand. But in books, this is not the way as this expression is written. In books, the way as this expression is written is this. Somebody very mean, very bad, try to confuse you and put this stuff in a book and say, oh, you are a big boy, so you know differential equation. And if differential equation is used, this is the equation of motion. Equation of motion of any body. This is very complicated, much more complicated than this, but both are the same thing. Differential equation, and you will see differential equation is written. For sure. You will see differential equation. Differential equations are the same as integrals. Okay, but a little different. Okay? It's not trivial. It's not trivial. I want to tell you that I'm not trivializing calculus, just trivializing. I'm doing calculus very trivial. But what I'm trying to tell you is that calculus is not mysterious. It's not a mysterious thing. Calculus have an intuitive root, and the root is in physics. Physicists invented everything. Calculus, just calculus. This is invented calculus. Okay, this is a differential equation and is equal to this. But there are another differential equation. For example, this is the differential equation that describes, this is the differential equation that describes the motion of a rocket. I don't know, something like this. V k multiplied by v equal to 0. This is dx dt. This is the equation of motion of a rocket. The Saturn V, the shuttle going to space. This is the equation that tell you which is the distance traveled by the shuttle at each time. It's very hard to obtain from here an integral, very hard. But I swear to you that this is an integral. At the very root, this is an integral. The differential equation course is a course to know how to convert this in an integral, how to convert this in a result that is very easy to see from an integral. So don't be afraid about differential. Okay, these two here. What does these two here means?
The second derivative.
The second derivative. What is the second derivative? Oh yes, the second derivative. What is the second derivative? The second derivative is the variation of is the velocity of the velocity. You know, acceleration. What is acceleration? Acceleration is the variation, the velocity of velocity. But since the velocity is the velocity of the space, so some guy trying to get some girls invented that this d multiplied by this d is d as square. But when you multiply this, you don't put d squared t, but d squared. Oh my God, this guy is very intelligent. So the answer is that this square means the velocity of a velocity of a velocity of a velocity. And if you find a 4 here, is the velocity of a velocity 4 times. A number. No. This is a differential equation. This is an expression you will see next week. And when you see this, oh my friend, what I'm doing here? This is not my play. I will not be an astronomer. What is this? This is probably the most important quantity for any observational astronomer. The most important quantity. In this quantity is hidden all the secrets in light emitted by a source or detected by a telescope. This is called the specific intensity. The specific intensity of light. And what all this D means? What all this D means? What is it? The same that this dx is a small piece of x, but dx divided dt is a long piece of x divided by a small piece of time. This is how much time, space you advance in a given amount of time. This is how much energy a body emits per square meter per second per solid angle and per wavelength. So it's just something like a rate of something. The rate of something is the velocity of something. The amount of something divided by small things, which are all these differentials here. So again, this expression is very confusing at first time, but when you understand what is behind this, you will not be worried about its meaning. One comment. Next week, Paulo, me, Ignacio, Juan Carlos will be available for all of you if you want to understand expressions like this and want to have an explanation, probably in Spanish, about what does this mean. Okay? So please don't be shy and please ask when you see something that you don't understand. Okay, finally. So please, can someone here even the advanced students, because here are students that are at the 7th semester. Can somebody tell me what the fuck is this equation? That you will see probably next week. This is an electron trapped around a black hole. I just see black holes and jets, astrophysical jets. This is also the electrons that emits radiation in Jupiter. Exact. This is the Lorentz equation. This from here is the Lorentz equation. The Lorentz equation is the Lorentz force. I'm sorry. The Lorentz force. The Lorentz force is the force that a charge feels when it's in presence of an electric field and a magnetic field. What is this? dr divided by dt. What is this?
What is R? What is R?
R is position. Very important. R, and please don't ask me why. R in physics is position. I have been prefer X or P, but these crazy guys in the history use R instead of P. So this is dr divided by dt. What the fuck is this? This is velocity. This is velocity. The x divided by dt is velocity. So this is velocity times magnetic field. This is the electric field. This sum means that the two forces sum up. And what the fuck this side of the equation means? Of course. The derivative, I don't know what the derivative is. So, the second derivative is the velocity of the velocity. So, acceleration. So, this is the acceleration, and mass multiplied by acceleration is force. So, this is the second law, the second Newton law. So, if you see this equation, you have to be able not to understand, fully understand it, and probably you shouldn't need to solve it. Okay, a secret, just a secret. I haven't been able, I am not able to solve this equation. Meaning, I'm not able to solve this equation, except if you give me a computer. I'm not expert on solving differential equations on computer. Give me any differential equation and I give you a solution. If it's a computer. But if you don't give me a computer but just a sheet of paper, no, it's not the solution. I will look for the solution in the books. Okay. Last topic. 10 minutes and last topic. You know, it's very hard to learn calculus if you use 3 slides or 3 courses of calculus. It's very hard. Okay. But at least you have a lot of questions. Everything that my teacher of integral calculus has taught me is true. These guys they are not taking my money out. Okay? You know, my friend, a lot of things just for a very, very simple things. Okay, that's our last topic, and you will be talking with Bernard about this topic next week. And this topic is about the fact that in mathematics there are complicated functions and simple functions. Very important. Know that in mathematics there are complicated functions and simple functions.
I think there are complicated and more complicated.
So, please tell me. This function is simple or complicated? This is very simple, yes? What about these functions? Is simple or complicated? Simple. Do you know what is E? Okay, somebody knows what it is. This function is simple or complicated? What about this function? Pay attention. This function functions are very important and was invented by astronomers. Do you know this function? This function is simple or complicated? Everyone has to admit that this is a very complicated. And this integral from here has a result. This is a sum. And the sum is called an elliptical integral. And they appear a lot in celestial mechanics. If you are a celestial mechanics expert, for example, if you work with the black holes, you are a celestial mechanics expert. The celestial mechanics experts are not people working with spaceships and planets. No, now the celestial mechanics experts are people working with a binary of two neutron stars. You know, we have here a celestial mechanics expert, and it's called Leonardo Pachon. You know Leonardo Pachon? Leonardo Pachon works with the atomic physics group, and he works on the orbit of particles around neutron stars. And they know, he knows a lot of celestial mechanics, but not the easy celestial mechanics, the hard celestial mechanics. The celestial mechanics related to general relativity. So, okay, the point is that among
The green one.
among functions are simple functions and are very hard functions, very difficult functions. So there is
Teacher, you have brain ink in your hand.
what in my head. Hello, my hand. My hand.
Teacher looked
What about my phone? This is bad. This is bad. Oh, fuck. Okay. You will tell me by this. Okay? So, there is a trick invented by mathematicians, and is that any function, pay attention, any function in the world can be always expressed as simple functions. Any function in the world can be expressed as simple functions. And the way as you express complicated functions in terms of simple functions are two ways. The third way it's called power series. Power series. Power series is a very important trick in mathematics, and it's a nightmare for calculus students. It's a nightmare. Power series, for example, teach us that e to the x is equal to 1 plus x squared divided by 2 plus x to the third divided by 6 to a to the 4 divided by 6 times 4 plus, you know, until the end of times. You need to sum up all these simple functions, and if you sum up all these simple functions, you get the exponential function. It's incredible. I don't know if you are amazed by this fact, but it's incredible. If you do the integral of e to the x, it's easy. But if I put e to the, pay attention. If I say you, please do the integral of e to the t to the square, what is the answer? The answer is that the integral of this can be calculated using this sum. Because e to the t to the square is 1 plus the exponent plus the exponent squared plus the exponent to the third divided by 6, right? And you know what is the integral of this? What is the integral of this? What is the integral of this? So you convert a very complicated integral in a sum of infinite integrals which are very simple. You know, this is the first way, and you can convert a complicated function in a simple function. And there are the second way, and the second way was discovered experimentally by Greeks. It's called a prism. The second way, as you can convert a very complicated function in simple function, is using something like power series. Power series, but not of this very simple x, but for example, power series of sine and cosine. You can express also the exponential, or you can express this very hard function, or this very hard function. You can express this function, for example, as sine x divided by 2 sine square x, I'm sorry, sine 2x divided by 3 minus sine 3x divided by 4. The sum of these functions also give you a very complicated function. This, yes, is some kind of series, of infinite series, but of sines and cosines. These series are called Fourier series. Fourier series. And before ending this very simple class, I want to explain you that this series is simple mathematics, but this series, oh my God, this is full of physics. This is physics to the fore. Okay? What does this means? The fact that a function can be converted in a sum of sine. Look at this sum. This is a way to put all the sum in a very compact form. And these numbers up here are just 1, 1/2, a third, a fourth, named A. A1, for example, or A0, there is 1. A1 is 1 over 2. A2 is 1 over 3. Okay? So you can express a function as a sum of sine. If you do a plot of what the function is, for example, the function could be this, the fact that this function can be expressed as a sum of sines means that this function is equal to the sum of this is sine, plus this is sine 2x, plus this is sine 2x. And if you sum these functions, you can obtain almost any function in the world. This is powerful. Very powerful. Your shape, your face, is a sum of sines and cosines. Wow. It's incredible. So, this is also just mathematics. But if you think in physics, this shape is like waves. And this is a wave with a wavelength. This is a wave with a shorter wavelength. And this is a wave with a shorter wavelength. And if you think better, and if this, for example, is a signal, this is a signal, this is the voice of your mom. Oh, this is the voice of your mom. You can tell your mom this night that the voice of your mom can be divided in very simple sounds, having a very unique wavelength. In music, this is called a note, a pitch. Okay? This is called, for example, this could be do, this could be re, and this could be do re mi. Actually, in English, it's something like A, B, C. Yes, they are crazy. They are crazy. I was talking. I was talking with a friend of mine from Germany, Rene. Something like this, something like that. Please, man, don't be hard with me. Okay, that's this guy. Oh yeah, incredible. You are very good musician, very biased. Okay? So, the voice, whole head, can be divided in a beautiful do, a beautiful re, a beautiful mi, and at the end, your voice producing music. So, this is magic, this is magic, this is beautiful. You know, the composition, finding which waves, which terms in this song sum up your signal is made by your cell phone. Each time you talk with your cell phone, a chip in your cell phone divide, decompose your voice, and obtain not the waves, but these numbers. These numbers. How many numbers of these need to be for my voice to be reproduced at the other side? Not too many. If you use just 4 terms in this sum and send just these numbers, as the cell phone of the other guy or the other girl at the other end will receive these numbers and create again my voice. That's why your voice is not exactly like your voice. You sound very different in a cell phone. That's why a cell phone that don't use every coefficient. If a cell phone was able to use every coefficient, your voice will sound exactly like I am talking. With an analog telephone, it's different, because an analog telephone converts your voice from being a sound wave in an electrical wave that is transmitted to the wires. This is very different. These don't transmit electricity. These transmit numbers. 0, 1, 0, 1. And with numbers, you only can transmit numbers. Numbers, not signals, numbers. This is Fourier analysis, and it's very important. If this is light, this is colors, and this is the decomposition of light in colors. Knowing about Fourier series, knowing about Fourier decomposition, Fourier analysis is very important for astrophysicists, and you will learn a little, because Bernard will not explain in detail what Fourier analysis is, but you will learn a little next week about Fourier analysis, because Fourier analysis is very important for ranging from spectral analysis to interferometry. To do interferometry, you have to know about Fourier analysis. Okay, this is my summary. This is my summary of the basic mathematics that an astrophysicist should know before being an astrophysicist. Okay, this lecture has been recorded, video recorded, and I will try to send you before Monday a couple of readings, very simple readings about all this stuff that you can prepare, that you can read before astrophysics classes start next week. Okay? I love you so much.
So, we're ready to be an astrophysics.
So you have to send me. Thank you very much. The video is in YouTube, or this is a live stream. You have to be long, the live stream.